Hi everybody, thanks for coming. Today I'm going to talk all about liquid cooling, why it's important to start getting prepared. It's something that not a lot of our customers today are fully experienced with, but learning today hopefully see what we're planning, kind of why liquid cooling is important, and where we're going to be going as a group. So the big thing I always like starting off with is power. There is a major shift happening in our industry and where chip density is going and rack density in general. When we look at kind of average racks throughout the entire industry, this is not specific to HPC or AI or enterprise, this is kind of everything everywhere, where are the rack densities? Some of this, to me, somebody who comes from HPC, is relatively low, but this is the reality of where the rack densities are across the whole industry. Now, what does this actually look like? What are in each of these buckets? Well, when we look at kind of a 10 kilowatt and below, this is a very small number, maybe even single-digit servers, like DL360s or an XD685 in our AI portfolio, but a very small number. When we start looking, though, at full rack scale solutions, that's where we start entering this 30 kilowatt space and above. And that is where liquid cooling really shines. Now, the other thing I always like starting off with is where are we going, right? If we look at the average density today, we kind of peak at around 10 kilowatts. What's really interesting is as chip density increases, so do the racks. And we're starting to see this shift of the average rack density start moving towards around 20 kilowatts. But what's really interesting is this kind of 50 kilowatt space and above is also growing very quickly. And that's what we'll be talking a lot about today. Now, for the last decade, a lot of the chip densities have been increasing at a fairly expected rate. But in the last 5 years, chip density has gone up exponentially. So not even that long ago, a top-bin CPU SKU might have been around 250 watts, maybe topped out around 300. Today, we have CPUs available over 500 watts and GPUs over 1,000. So 1 kilowatt GPUs in a very small package. Imagine what happens when we put 8 of those inside of a 1U server. Thermally cooling is going to be very challenging with an air-cooled solution, and liquid cooling makes a lot of sense. Something we don't often talk about, though, and this is an important part of the liquid cooling story, is how these chips are being designed. In the past, T-case, or the maximum thermal case temperature of the silicon, could go up quite high. We often would see CPUs or GPUs be able to go up to 100 Celsius, and they would still work for the most part. Today, we're actually seeing, anywhere we see a really sophisticated chip design, so something with high bandwidth memory or some kind of super chip in some way, where there's a lot of technology packed into a small space, what you can start to think about is there's more technology stacked on top of one another, and we have to penetrate that entire stack of technology, which means it's going to be less tolerant of heat overall, and air cooling puts that in a pretty tough spot. And so that's why I made this intersection drawing to show at a certain point, we can't use traditional air cooling technologies because the chips are so sensitive to heat. We really have to make that shift towards liquid cooling. Now, the story on liquid cooling. The easiest part of this is really the top part of this triangle. This is what we talk about at exascale when we talk about big AI systems. Liquid cooling enables big, powerful chips to run for long periods of time, right? That's like the easiest part of this story to tell. What is really gaining a lot of airtime is around efficiency. Data centers are starting to look at not just the power consumption in the server itself, but they're starting to look at the entire rack infrastructure all the way out to the data center. And so you can imagine you have, let's say, a 5 megawatt data center. And traditionally, you have expected, say, a PUE of 1.7. So there's a certain amount of that power that's going to go towards the cooling infrastructure, and a certain amount of that power that's going to go towards compute. Well, customers don't want to spend 1.7 times the compute in cooling infrastructure. We want to get that as close to 1 as possible, which means it unlocks more space for more compute. And so that's part of the discussion we're seeing today. And then the other part is, from the CFO angle, we just want to spend less. We want to pay way less for cooling, and we can do that through part of this liquid cooling story. And then the other third part of this, which is kind of combined, it has a performance element and efficiency, is density. If you think about the data centers that you work in today, especially if they're air-cooled, my guess is they are almost always half populated or less. Many of the data centers I've been through have a power capacity of around 17 kilowatts. This could be 5 to 10 servers in a 42U rack. That's a ton of empty space. In HPC data centers, or especially ones that have a focus on AI, we're fully populating racks, which means if it's a greenfield, we could build smaller data centers, more concentrated infrastructure, but there's also a lot of performance benefits when we can bring all the networking much closer, lower latency, kind of a better story overall. So let's go back to the kind of bar graph I showed, the different buckets, what's happening with different technology. It's important for me as a product manager, so I'm the liquid cooling global product manager, to not sell liquid cooling for liquid cooling's sake. It makes no sense for us to put liquid cooling on a 500 watt server. It makes no sense for us to try liquid cooling a 15 kW rack or less. There's really no ROI on it. The infrastructure would make no sense for us to pursue that. And so I always like stating that right away. If you have racks in the data center that are 20 kilowatts or less, an optimal strategy is really how can you increase the energy efficiency of the infrastructure you have. Pursuing liquid cooling is going to have some OpEx costs. And so this is pretty typical. Again, a handful of ProLiant servers, maybe one of these AI boxes. These can be about 10 kilowatts a box, but those almost always are going to have an air-cooled option. When we do start talking about liquid cooling, it's really beyond 20 kilowatts. And so this is where we start seeing technologies that are mature, that increase energy efficiency, and you're going to use liquid cooling in some way. And so, for example, this would be something like a rear door heat exchanger, an in-row cooler, or our ARC's adaptive rack cooling system. And so the main principle behind this technology is we're going to take facility water, kind of a cold water loop, something that is going to be chilled from the data center, and we're going to pump it directly into a coil that's going to sit very close to the IT. So a rear door is very simple to explain, and it's really in the name. It sits on the rear of the rack, replaces the rear door, bolts right on, and it provides an interface where the server heat is actually pushed or sucked through this coil, and it's cooled back down. So if your data center has thermal issues today, really just from the HVAC system is reaching its limits for air exchange capabilities, this actually brings that air temperature back down. And so if you ever stood in a data center hot row where the rear door heat exchangers are installed, it's like average room neutral temperature coming out. It's coming out with velocity because there are fans assisting it, but it is not hot at all. And that's the purpose of a rear door, alleviating the pressure on the data center. Now ARCS is kind of a one step further. We're still pumping in this cool water directly into the coil, but instead ARCS is actually creating that cool air on the inlet side for the servers to suck in, pushes all of that hot air through the coil, and then it sucks it back into the ARCs. And so this is actually a completely enclosed infrastructure that can scale up to 4 racks, where it's using liquid. I still call this liquid cooling, but it's more of a liquid to air cooling solution. So much more energy efficient than, say, perimeter cooling, cracks and craws, and we can get much higher rack densities. When we really start talking about liquid cooling, if somebody says, are you investigating liquid cooling? Are you using liquid cooling today? They're most often always talking about cold plate cooling, direct liquid cooling right at the chip. And so for me, this really starts to become a serious consideration beyond 40 kilowatts. And so this is maybe a handful of HPC or AI servers. It could be a full rack of ProLiants, but that's really where we start to enter this space. And so what does this stuff look like? The real nuts and bolts. Well, in almost all cases, we're going to have cold plates sitting directly on top of the CPU or GPU, pumping that heat away. The numbers really vary, and so I always put kind of the approximate symbol here, but in general, 80% of this server heat ends up getting captured by the DLC system, or the direct liquid cooling, and 20% still needs ambient air cooling. Why we don't always go to 100% in these rack densities is really about flexibility and cost. When we look at a server like this is our XD685, this is an 8-way GPU box. The GPUs and CPUs are liquid cooled, but you notice the DIMMs aren't cooled, we're not cooling any NICs, and it's because we want to provide tons of options for you within that box. If everything was liquid cooled, the amount of options in the portfolio would be very small, because we have to design special coolers for each one. But the GPU sockets don't really change, and so that's why we always do liquid cooling. Now the pieces of technology, this has really been an interesting space, is what do you use for a coolant distribution unit? This is the primary infrastructure that provides interface to the data center. It comes in two flavors, and this would be my kind of main education for you today. It comes in rack CDUs or row-based CDUs or standalone CDUs. And the major difference is, how are you planning on growing your infrastructure? If you are a data center that buys 1 to 2 racks a quarter, you like to try different vendors, different technology, and scale over time, in-rack CDUs are amazing because each rack is standalone. You could have 1 rack of CDUs, or 1 rack of CPUs, sorry, 1 rack of GPUs. You could have vendor A, vendor B. It could all live in harmony in the data center because each one is using an in-rack CDU that provides the interface to facility water but isolates it. So if there's any issues, you turn a rack on or off, it doesn't matter, they're all self-contained. If you are deploying big rows of infrastructure at a time, you're building big homogeneous clusters, you're building an AI factory, you're doing weather prediction, and you need a big chunk of x86 systems all chained together, row-based CDUs work really great. Better economies of scale over the CDU. It's a little bit cheaper. We can build in redundancy a little bit better, chain these CDUs together. But the downside is, the CDUs often can't tell the difference between what's in these racks. So if you have a big, hungry GPU rack, needs a lot of flow, beside a CPU rack that's running on idle, the big CDU might overcool some racks and undercool others, unless you're doing a lot of manual flow setter valves. And so that's kind of the main difference between these two. Now the other piece of this is around intercompatibility in the data center and what's being standardized. Now, I always get this question, if we buy from vendor A or vendor B, how does it all work in the data center? Well, the nice thing is all the CDU vendors have made this very easy. All of the connection points that are coming out of this CDU, either in-rack or row-based, are super standard. You can actually find all of these connections inside your favorite brewery. They're all sanitary flanges, tri-clamp connectors, all food-grade safe, stainless steel. So what they're connecting to in the data center is very standardized. There's nothing real proprietary happening here. And so I kind of re-emphasize this here with the connections, whatever you're buying from vendor A or vendor B is going to work in this data center. Now the last bucket, this is kind of the high end, and this is a really interesting space, especially with AI and where we're going next, is racks beyond 100 kilowatts. We actually have on our booth today the new HP Cray GX. Those cabinets are 400 kilowatts each, and we're going to chain 4 of them together with a big 1.6 megawatt CDU. We do cooling in a few different ways in this space. One, we'll either do direct liquid cooling alone, and the data center has to capture that final 20%, or in many cases, we actually will marry something like a direct liquid cooling system with a rear door or with an ARCs. And so this kind of demonstrated system is using direct liquid cooling on all the GPUs, and then we're putting all of those racks inside of this ARC system. And so it's actually capturing that final 20 to 30%. And so there's no excess air thermal footprint on the data center around it. The other way we do it is we actually design cold plates on everything. And so you can see this demo on our booth today. This is a visual of the current Cray EX system. And our new GX, which is launching this year, we use cold plates on everything. Voltage regulators, memory, GPU, CPU, all the capacitors, all the resistors. They're all touching a cold plate that has fluid moving through it actively. And we can get very high heat density with excellent thermal efficiency. So why us? We have been doing liquid cooling for several decades. And I always love showing off this visual because it really shows the timeline of our expertise and the partners that we work with. And so when you look all the way back to the 70s, Cray, SGI, and HP, we've been doing work with refrigerant-based systems, immersion cooling, single-phase, two-phase. We've really explored it all, and helps drive us to our hardened position of what we're doing with liquid cooling today. Now the ways to get into liquid cooling. This is one of the areas we often spend the most amount of time with is, your data center might be looking at the next chapter of where you're going with your data center. Do we want higher rack density? Do we want to invest in AI? What does this all mean? Well, to me, these are the 5 ways you can really get into this space. The most common one, to me, is new data centers. It is absolutely the easiest to build from the ground up, because often when we need liquid cooling, we also need big power. This means 415 volt, 480 volt, in Europe 400 volt. We're not talking about 208 because we really can't get that rack density. We want to move to higher power levels. It's often easier with new data centers. The other way, which is very exciting because we have a full demo on it, is modular data centers. So imagine your data center that exists today. We don't have to touch it at all. What we want is to pour a concrete pad, power, availability, networking, and we will roll in a modular data center, fully kitted out, liquid cooling pre-installed, and that infrastructure is totally self-contained. That's one of the fastest growing avenues we have for liquid cooling. Retrofitting, I find, is actually not very common. I find once you're trying to contemplate the red tape, we have to bring infrastructure down, we got to knock walls out. Often it is going to be much easier to find the budget to either move into a colo or build your own data center, and that's where colos become part of this. I'm finding this is one of the fastest growing areas where colos are trying to really market themselves as big power, liquid cooling ready. And so you're going to see a lot more data centers in the EU and in North America proposing and really pitching themselves as like AI ready for big infrastructure. Now, who are these customers? This is one I always love talking about. Simon McIntosh in the UK, they just deployed in an 8-month period a 5 megawatt AI-focused liquid-cooled data center, all modular. And so this infrastructure from kind of signature sign to onboarding took less than 1 year, and it was all modular. This is a really exciting use case of where speed and AI were both part of the mission. When we're looking at weather users are one of our highest users of liquid cooling, especially when they're looking at something like rear door heat exchanger or ARCs. They're looking for a lot of flexibility from their cooling infrastructure, but they are still buying a lot of x86 stuff, right? They're not buying tons of GPUs. They want a lot of classic workloads, but they are still increasing the rack densities when CPUs are 500 watts. Heat reuse is really interesting. In the EU, there's a couple notable cases where customers are actually taking their liquid-cooled data centers, taking 40 Celsius facility inlet, so pretty warm, non-chilled water, and they're taking out 60 Celsius water out the back of the supercomputer or AI system and using it to heat their greenhouses, melt snow on the sidewalk, assist the HVAC inside of the infrastructure. And that first slide I showed you with Simon, that is part of their plan. They have all the hooks in place to do heat reuse. Automotive. This is another interesting one where we're seeing several customers using DLC in automotive manufacturing. So they're doing a mix of CPUs and GPUs, simulation, classic workloads, but they're trying to build in existing data centers that are smaller but maximize their floor space usage. So this is a real solid density play and one that we do a lot of. Now to bring this all home, right? We talked about the stuff, we talked about the density, but I really want to bring this back to why HP is a good partner in this space. Where we build this stuff matters a lot. In the US, we have a specialized facility just around bringing up large water-cooled infrastructure that has multiple megawatts of power capability, where we actually build every US-bound DLC system, fully rack it, fully cable it, benchmark it, fill it with liquid, put it back in the crates, and ship it to customers. And so we do no on-site builds of liquid-cooled infrastructure. We pre-build all of it. Whether the system is 1 rack or 50 racks, we will pre-build it, wire it, power it, run it, and ship it to you knowing that it works, and our teams will assist it to the setup. And in Europe, we also build in Kutná Hora, Czech Republic, same thing, full rack and roll, and this is where we deliver all of our global systems. And the last one here is around service. These systems, when are fully loaded, full racks, 100 kilowatts, are not cheap. And so it is critical that these systems are running full-time, high reliability, high uptime, and working with the support team matters a lot. We ship our teams globally to all of our support sites, working directly with customers in a few models. We do a ton of white glove. That is the pure Cray high-end system. We go with every system, ship engineers, we make sure it works every time. But we also do a lot of tech care where we train you. So customers that are looking to kind of take on some of the service responsibilities, meet the kind of minimum requirements, we also do a lot of train the trainer. So something that we really love doing today. Now, kind of wrap this up, where you're at Discover, there's a lot of options to actually touch and feel the technology here today. So we've spread out all of our DLC stuff throughout the floor, so absolutely, please take your time, come find us, come see what a DLC system looks like, the big CDUs, you can touch and feel them. I think it's important to understand the size of this infrastructure and what it actually looks like inside of a server. Some of it you'll actually see serviceability of taking a DLC server in and out is really no different than an air-cooled server, other than 2 dripless quick disconnects. Otherwise, acts exactly like an air-cooled system, so touching and seeing is believing. And then the last thing is checking out the rest of our demos. We're doing a handful of liquid cooling sessions, demos, and so I'd love to see you again at one of these sessions or just even at the booth. So with that, thank you so much for coming. I hope you have a great rest of your Discover.